Swayam Prabha. Digital India. Educated India.
So, hello everyone, today I will start module 2, adhesion and wetting phenomena, and the first lecture in this module will be surface tension and surface energy. So, before that I will quickly rewind the last module, that intermolecular forces. In the first lecture we discussed various intermolecular forces starting from 4 forces of nature, that was the starting from the gravitational and electromagnetic forces and short and long range forces. Then we discuss historical perspective of various intermolecular forces starting from 17th century to the 20th and 21st century. Then we discuss the pair potential, which is having both attractive and repulsive intermolecular forces. Then in the next class we discuss the classification of various intermolecular forces depending on their opposite nature, short range, long range, attractive, repulsive, and also we saw the classifications based on the origin, electrostatic, then quantum mechanical and entropic. Then we discussed the expression of few intermolecular forces. So, we started with strong intermolecular forces like covalent interactions and van der Waals interactions, electrostatic interactions. In the van der Waals we discuss specifically van der Waals dispersion forces and steric repulsion. Also we discussed a few other these hydrogen bonds. It is like a ion dipole interaction between hydrogen ion and electronegative atoms, and then hydrophobic interaction where non-polar molecules come into contact with the polar molecules. Then in the last class we discussed the thermodynamic aspects of this intermolecular interactions. We saw how the pair potential is related with the self energy, and also very interestingly we derived this Boltzmann distribution and chemical potential and Boltzmann distribution. We related the intermolecular interaction with the solubility, we related this intermolecular interaction with other physical and chemical properties as well. So, in today's class we will start how do we define the surface tension and surface energy, then we will see the thermodynamics of surface tension and surface energy. Also we will see the surface tension between the two liquids, surface tension between liquid and solids, and as well as the surface tension between the 3 mediums 1, 2 and 3. So, to start with, first we will see, as I told, we will see the interaction between 2 different mediums 1 and 2. So, the first thing when there will be interaction is it is called the work of adhesion or the cohesion. The work of adhesion and cohesion are the reversible work done or free energy changes to separate the unit areas of two surfaces or media from the contact to infinity in vacuum. Means the work done for the change in the unit areas or media from the contact to infinity in vacuum. So, means the work done for the change in the unit area, that is work of adhesion. So, you can just see here, if this is the work is done between the two different media like 1 and 2. So, this is called the adhesion, and if it is done between the two same media or two same surfaces, then it is called the cohesion. So, gamma W1 2 it will refer the adhesion, but if you write W11 it refers the cohesion. So, how do we write W12? If 1 is solid, 2 is liquid, so we write work of adhesion solid liquid. If 1 is liquid, 2 is solid, we will write work of adhesion liquid into solid. So, this is how we refer this work of adhesion or the work of cohesion. So, what we are seeing here is this is media 1, this is media 2 and this is the unit area. So, whatever work is done to separate these two, that is the same as the work of adhesion. So, we are defining in the either way or you can say in the reverse way, that how much in free energy or work need to be done if you want to separate the unit area of two medium 1 and 2, or you can say 1 and 1. So, from the work of adhesion, now we will define how we relate this with the surface energy or the surface tension, because this change is taking place at the interface. So, free energy change when the surface area of medium is increased by the unit area. Now, the process of creating unit area is equivalent to, as I told in the reverse way, is separating two half unit area. So, as we are separating the two half unit area, so that is why the work done will be W11 upon 2, and this is equivalent to the surface tension. So, gamma is the surface tension is equal to the half of the work of adhesion. Now, atoms and molecule at the surface of liquid and solid possess more energy than those in the interior. So, it simply says that is why these liquids or solid possess the surface energy, because their energy at the interface at the surface is always higher than that in the interior. Now, if you remember the last class we discussed about the work of adhesion, or you can say we discussed about the self energy, and the self energy was defined as mu I liquid proportional 7 times K T B. K is Boltzmann constant. Okay. So, what it says is, if the intermolecular interaction is high, it means it is going to have the higher boiling point. Now, as we can see, this work of adhesion is directly related to the surface tension or surface energy. So, we should have the similar observation in terms of surface energy. So, here it says that substance with high boiling point will have the higher surface energy. So, I have listed 3 examples. For mercury, the surface energy is 485 millijoule per meter square and its boiling point is 357 degrees centigrade. Next is the water, it has the surface tension of 73 millijoule per meter square and its boiling point is 100 degree. But if you go for the argon, its surface tension is decreasing to 13.2, at the same time its boiling point is also decreasing. So, it says that surface tension is directly related to the change in the free energy. Now, we will just see one example here. Let us say you are having a soap film which is fixed between the two wire and one side is fixed. So, it can only move in one direction, and if you want to move in one direction. So, you have to apply a force F. We are applying a force F over here, and where we are applying, this is the length L. We are applying this at the length L. So, the work done will be force into displacement, and force will be what is the surface tension into it is applied on the length L. So, this is the force F into dx, F into dx. Now, again length into dx we can write in terms of dA. So, this it says that work done is equal to the surface tension, or here you can say surface energy into change in the unit area dA. Now, from here you can quickly see what should be the unit of surface tension. So, surface tension, if you see from here to F upon L, so it says milli-Newton per meter, or if you want to write in CGS, so it write dyne per centimeter square, and in terms of energy or area it will be millijoule per meter square or per centimeter square. So, we will see the another experiment for a flat deformable interface A. This is the interface area. We are selecting applying a force F to the particular length L. At a particular length we are applying there, so that we are able to pull it out. We are able to pull it out to the delta x is the displacement or the distance. So, the change in the interface area will be L into delta x. Now, as you know, this surface tension is F upon L. So, work will be total work will be F into dx again here. So, F will be gamma into L into dx, or you can say F into. So, if you integrate gamma for the entire area, you should be able to calculate what should be the work done, or you can say the work of adhesion or change in the free energy for the change in the unit area. I have listed one exercise here. So, consider an amorphous amount of liquid which is initially in spherical shape at the radius of 1 micrometer. This liquid is immersed in the water, and interfacial tension between both are liquid and the water is gamma LL 20 millinewton per meter. Now, you have to calculate the energy required to double the interfacial area, energy required to double the interfacial area. So, if you remember the last, say it was W gamma into delta A. So, if you can calculate delta A, how to calculate delta A? We already have the sphere, its radius is given to us. What you want to do? You want to double the interfacial area. So, you have to calculate the delta A. If you can calculate the delta A will be 4 pi r square. In case of R1 will be 1 micrometer and R2 will be 2 micrometer. It is almost you are doing double. So, if you calculate it, delta A into gamma is already given to you 20 millinewton per meter. The answer will be 2.5 into 10 to the power minus 13 joule. Now, we will just see how the surface tension varies for the solids and liquids. So, for the solid, the surface energy is greater than the internal energy, as we discussed earlier in the last slide, as the free energy of outermost atoms is not nullified and they are not equally attracted in all the directions. So, first thing says the surface energy for the solid is greater than the internal energy, and if you want to increase the surface energy, you have to increase the interfacial area or the surface area. If you increase the interfacial area, you can increase the surface energy. And adsorption, if some foreign molecules are coming on the surface, it means they are going to reduce the surface energy. If some foreign molecules are coming and sitting on the surface, means they are going to reduce the surface energy. And for the liquid, we call typically it is a surface energy is called surface tension. I, the attraction force exists between the surface molecules of the liquid. Surface molecules of the liquid get further apart with the loss of molecules, causing the increase in the net attraction between molecules, when in this case they will have the high surface energy. So, this can be tuned by some external means like change in the temperature, change in the pressure, and liquid tend to reduce the surface energy by minimizing the surface area. So, in case of liquid, they try to reduce the surface energy and try to collapse or minimize the surface area. So, this is the difference between the solid and liquid because of their intermolecular interaction. The intermolecular interaction is much stronger in solid as compared to the liquids. So, in general it says if it is a higher surface energy means there is a higher adhesion strength between the molecules. These are the few examples where we see the role of surface tension or surface energy in on daily basis. So, basically metals have high surface energy and thus easily get wetted by the suitable adhesive. So, metals and adhesive are being used for the various applications. Next is the waxes are not easily wetted because they are having the low surface energy. So, whenever we want to prepare the surface should not be wetted, we see there is a coating of waxes. Also the Teflon is having low surface energy, that is why it is not going to be wetted, and we usually see it is applied in the non-stick cooking utensils. So, these are the few examples which we see are applied on the regular basis, but as I told, the higher surface energy means higher adhesion strength of the molecules. So, we quickly rewind how the surface energy related with the internal energy or enthalpy or the Gibbs free energy. So, thermodynamically the interfacial tension or interfacial energy is the increment in the energy or increment in the work done due to reversible expansion of the interface by a unit area. Now, it can be either at constant entropy, constant volume, constant composition, constant pressure. So, we will see if you remember the last lecture, in the last lecture we derived from the first law of thermodynamics that change in internal energy is equal to the dq plus dw. Now, dq from using the second law of thermodynamics you can write it into ds, and this dw will have mechanical work P into dV, interfacial work gamma into dA plus chemical work mu I into dNi. Mu I is the chemical potential and Ni is the number of molecules. So, from this expression, if you want to see define the interfacial tension or surface tension, so you can simply say surface tension is the partial change in the internal energy per unit area at the constant S, constant V and constant N. So, at constant S, V and these terms will be 0. So, you can simply say the surface tension is the ratio of change in the internal energy per unit area at these conditions. Now, H is equal to U plus P V. So, we can simply derive dH. So, dH will be du plus Pdv plus Vdp. If I write dH, so dH will be du plus Pdv plus Vdp. So, if I this is the du, here if I add these two terms, so we will get dH is, so Pdv will be cancelled out, we will get Tds plus Vdp plus gamma dA plus mu I dni. Now, from here again if you want to write the expression of surface tension at constant T p n n, constant T p n n. So, we are going to have two terms. So, dH upon dA minus T into ds upon dA. So, here it says change in the enthalpy per unit area minus T into change in the entropy per unit area. Now, in the same expression if I want to write at S, P and N at constant entropy, constant pressure and constant composition. So, you can simply write like this. So, this will be gamma is equal to dou H upon dou A at constant entropy, constant P and constant N. Now, from enthalpy now we can also calculate the Gibbs free energy. It says G is equal to H minus Ts. So, dG will be dH minus T ds minus S dt. So, here dH minus we have to subtract this. So, we will get the dG is equal to minus S dt plus Vdp plus gamma dA mu I dni. So, from here again at constant T p and n, constant T this term is 0, constant P this term is 0, constant N this term is 0. So, we can say surface energy is change in the free energy per unit area. That is what we are deriving since very beginning, that surface tension or surface energy is the change in the free energy per unit area. Now, free energy is the work done. So, work done F into dx, area L into dx. So, dx can be cancelled out. So, we derive from here gamma is equal to force per unit length, force per unit length. Also, if you see here, if you compare these two expressions, so it simply says delta G is equal to delta H minus T delta S. If you compare these two expressions, it says delta G delta H minus T delta S here. Now, from here you can apply the Maxwell relation to derive a relation between S, or you can say entropy and the surface tension. So, what does its Maxwell relation says? A into dx plus b into dy. So, we can write a partial derivative dou A upon dou I at constant x is equal to dou B upon dou x as at constant y. So, this is how we write the Maxwell relation. So, from here if you want to write the Maxwell relation between at constant T, P and N for the S. So, this will be dou S upon dou A at constant T, P and N, and this will be dou gamma upon dou T at constant A, P and N. So, here it will be the constant A, P and N, here it will be the constant T, P and N. and of course, there is a negative sign. So, it is the inversely related, not directly related. So, from here if you replace this dou S upon dou A with dou gamma upon dou T. So, here you can write surface tension is change in the enthalpy per unit area plus T times change in the surface energy per unit temperature. So, it says surface tension and surface energy is linearly related with the temperature. So, if I write the same equation here, H upon dou A plus T times gamma upon T constant A P and N, and this was the constant T P and N. Okay. This is the constant T P N. Okay. So, here I have listed the characteristic surface tension of few liquids. So, for water 72.8, N-hexane 18.4, ethyl ether 17, chloroform 28.5, benzene 29, mercury 484, and correspondingly change in the, or you can see the slope of surface tension with respect to temperature. This is the slope, and this is the change in the enthalpy per unit area. So, if these two parameters are known, we should be able to calculate the value of surface tension at any given temperature. So, it will be dH upon dA plus T at what temperature you want to calculate into multiplied by this. So, you should be able to calculate the surface energy of that particular liquid. So, for all the interfaces, surface energy decreases with increasing the temperature. Thus, higher entropy or interfacial region compared to the bulk phase. So, it says if you increase the temperature, then what will happen? There will be increase in the entropy at the interfacial region. So, it says dou S upon dou A will be greater than 0, it will increase, and if it is increasing, it means gamma upon 30 it should be less than 0, because they are negatively related. So, if you are increasing the temperature, so there will be increase in the entropy at the interfacial region, and if entropy is increasing means there will be decrease in the surface energy or the surface tension. Now, as I discussed, what we see is there is a linear relation between the surface energy and the temperature, and it says if you increase the temperature, the surface energy is going to decrease. So, in one experiment for the water, it says at 10 degree centigrade it has a surface tension of 74, at 50 degree centigrade of course it is decreasing, its value has come down to the 67.94. Now, can you calculate the surface tension as 25 degree centigrade? So, here we can assume it is following a linear relationship. So, we should be able to extrapolate at 25 degree centigrade. So, what value is given at 10 degree centigrade? Value is 74.23. At 25 degree centigrade we have to calculate, and at 50 degree centigrade the value is given as 67.94. So, I should be able to calculate gamma at 25 by very simple interpolation. So, if I want to consider the linear, I want to do the interpolation. So, it will be 25 minus 10 divided by 50 minus 10 into 67.94 plus 50 minus 25 divided by 50 minus 10 into 74.23. So, this is very much simple linear interpolation. We are considering the surface energy change linearly changing or linearly decreasing with the increase in the temperature. So, its value will come out to be 71.9. So, it will be like 71.9 here. So, it is coming of course in between these two values. So, we will see one more example here. So, what it says, we are increasing the temperature in the range of 10 to 40, 10, 15, 20, 25, 30 and 40, and this is the decrease in the, if you are increasing the this, there is a decrease in the surface tension. Okay. Now, from the previous concept, can we calculate the differential surface enthalpy and differential surface entropy at 25 degree centigrade and 1 atmosphere. So, if you want to calculate differential surface enthalpy, or you can say if you want to calculate the differential surface entropy. So, if you remember the last exercise expression, so what it says, the surface tension is a function of dH upon dA at constant T p n plus T times delta gamma upon delta T at A p n at constant area, pressure and composition. So, if you apply this expression, so this again can be related with the delta S. Now, let us write these two expressions there, then we will be able to understand delta S upon delta A. So, what it says is dou S upon dou A to minus dou gamma upon dou T. So, if you plot between, this is the temperature and this is the interfacial tension. So, you should be able to get the slope will be the dou gamma upon dou T, and if the slope is known to you, you can easily calculate what will be the differential change in the entropy. So, this will be the same delta S upon delta A, and once this delta S upon delta A is known to us, we should be able to calculate the differential enthalpy. How to calculate differential enthalpy now? It says gamma is equal to dou H upon dou A plus T times, if you remember the last expression, gamma upon T. The slope is known at, you have to calculate at 25. So, T is 25, surface tension value is given at 25, surface tension is the 72, we have to calculate this value, T will be 298 into plus slope value. So, you should be able to calculate differential enthalpy as well. So, you will be able to get this answer. So, this is exactly the negative of the slope. So, it means the slope will be coming minus 1.346 into 10 to the power minus 4 joule per Kelvin per meter square, and this is the delta H upon delta A 112 into 10 to the power minus 3 joule per meter square. Now, next part it says calculate the work required to reversibly expand the surface at 25 degree centigrade and 1 atmosphere. Now, here it is saying can you calculate the W. how to calculate the W now here? Calculate the work required to reversibly expand the surface at 25 degree centigrade and 1 atmosphere, or you can say it is saying the calculate the heat effect due to this expansion. Now, can you how will proceed for this? Let us go back again. What it says? Yes, so it says the work done is equal to gamma into dA, gamma into delta A, and if you are talking in terms of change in the surface tension or surface energy, we can consider delta A is unit area 1 meter square. So, W will be very much same as the gamma. So, at 25 degree centigrade the value of gamma is 72. So, we are going to get the same value of the work done. So, I will write here W gamma into delta A, and delta A you are considering as 1 meter square. So, these are the two exercises. The surface tension of n decane varies with the temperature according to the expression given. So, it says gamma equal to 50.8 into 10 to the power minus 3 minus 9.2 into 10 to the power minus 5 T. So, now if I remember the thermodynamic expression for the interfacial tension, it says gamma equal to dou H upon dou A at constant T P n plus T times dou gamma upon dou T A P and n, and same thing can be rewritten as in terms of enthalpy dou H upon dou A T P n minus T times dou S upon dou A T P n. So, here we are replacing this with Maxwell relation. So, now next what it says, the one drop of n decane of radius 0.5, R1 is 0.5 centimeter. It is divided into 10 small drops of equal size. It means if you just see the volume of one sphere or one drop, 4 by 3 pi R1 cube equal to 10 drops, 10 into 4 by 3 pi R2 ka cube. So, here we will get the value of R2, that will be coming out 0.232 centimeter. Now, the first part it says you have to calculate the work performed on the system. It means W equal to gamma dA equal to gamma delta A. Now, if you want to calculate the value of delta A, so delta A will be area of 10 new drops or 10 smaller drop, 10 into 4 pi R2 ka square minus 4 pi R1 ka square and this will come out to be 363 into 10 to the power minus 6 meter square. Now, delta A is known, gamma is already function of temperature. So, at temperature at 20 degree centigrade means 293 K, at 293 K we can calculate the value of gamma. And so, work will be W equal to 50.8 into 10 to the power minus 3 minus 9.2 into 10 to the power minus 5 into T is 293 into delta A, and delta A we have already calculated. So, W will be 8.66 into 10 to the power minus 6 joule. Now, next part says change in the entropy of n decane. So, here if I compare the expression 1, let us say this is 1 with the expression 2. So, what we see is dou S upon dou A equal to 9.2 into 10 to the power minus 5. So, simply delta S will be 9.2 into 10 to the power minus 5 into delta A, and delta A we have already calculated. So, now the value of delta S will be 3.34 into 10 to the power minus 8 joule per Kelvin. Now, the third part it says the maximum heat exchange between the n decane and its environment, means we have to find the value of Q, and Q is equal to T delta S. So, value of T is 293 and value of delta S we have already calculated. So, the value of Q will be 9.68 to 10 to the power minus 6 joule. Now, we will see what is interfacial energy. So, here we are seeing interface may be between liquid or you can say the solid and two solids, okay, or you can say solid liquid interface. But in most of the cases, if you are talking surface energy of the liquid or the surface energy of solid, that is also interface, but there we are interface considering between the air. So, if we are saying the surface energy of water is 72, it means it is the surface or interfacial energy of water with the air is the 72 millijoule per meter square. But here we are going to consider either the liquid interface or the solid liquid interface. So, in case of liquid interface, particularly it should be the immiscible. So, if you are having two immiscible liquids 1 and 2, they are brought into contact. So, their free energy change is gamma 1 2, and this gamma 1 2 will be written like work of adhesion of 1 1 plus work of adhesion of 2 2 minus there will be some work loss for the interface or work of adhesion between 1 and 2. So, there will be half of the work of adhesion, or you can say the half of the work of adhesion means surface energy. The surface energy of gamma 1, surface tension gamma 2 minus there will be the loss of work at the interface between 1 and 2. So, this is the work of adhesion between 1 and 2. So, this is how we define the free energy change between 1 and 2. So, half W 11 is gamma 1, half W 22 is the gamma 2 minus W 12, and this is also known as the Dupre equation. Now, let us consider in terms of solid liquid interface. So, this 1 will be the, in case of solid liquid, gamma 1 will be solid, 2 will be the liquid. So, gamma solid liquid we can write gamma 1 means gamma solid, gamma 2 gamma liquid minus W solid liquid. So, here gamma solid means gamma solid refers gamma solid vapor, gamma liquid refers gamma liquid vapor, and if we are getting negative value of gamma liquid, it means the interfacial area tends to expand infinite, or you can say either way 1 and 2 are the miscible. If a solid is miscible in the liquid, then we are going to have the negative value of the solid liquid interfacial tension. Let us say now we are having a third medium, changing the energy of two dissimilar medium 1 and 2 into the third medium. Now, it will be the work done between 1, 2 and 3. So, work done into 1 and 2 and 3 will be, first will be the W 11, 1, 2, 1 and 2, then W 33 minus the work will be done between W 13 and W 23. So, W 12, W 33 minus W 13 minus W 23. So, if you remember W 12 will be gamma 1 plus gamma 2 minus gamma 1 2. So, if you write here W 1 3 2 will be W 1 2 means gamma 1 plus gamma 2 minus gamma 1 2 plus W 33 will be simply the, this is the cohesion, it will be simply the gamma 3, that is it, minus W 13 will be gamma 1, gamma 3, gamma 13, gamma 23, W 23 will be 2, 3, gamma 2, 3. So, if we just see here, this will be the cancelled out, this will again be cancelled out, this is again cancelled out. So, we are having gamma 2 3 plus gamma 1 3 minus, how it is left, let us recheck again, gamma W 1 2 gamma 1 plus gamma 2 minus gamma 1 2, W 33 it will be the simply gamma 3, W 13 gamma 1 minus gamma 3, W 23 gamma 2 plus gamma 3 minus gamma 23. So, what we are seeing over here is work of adhesion between 1 and 2, work of adhesion between 3 and 3. So, and how much it is separated, interaction is taking place with W 13 and W 23. Okay. So, because this will be if you just go to the previous slide, so it says W33 will be the 2 times of the gamma 3. So, all will be cancelled out. So, we will only have left with W132 is equal to gamma 13 plus gamma 23 minus gamma 12. So, if you are having 3 medium, then this will be the expression for the work of adhesion, or you can say the interfacial tension. Now, we can have the 2 situations. In one case W132 may be positive, in one case it may be the negative. If it is negative means, what does it mean? If it is negative means gamma 13 plus gamma 23 is less than the gamma 12. It means there is a repulsion between 1 and 2 in the 3. So, that is why the gamma 13 and gamma 23 will be lesser than the gamma 12. So, if it is negative value of, or you can say minus W132 is also referred as spreading coefficient or spreading pressure, sometime it is denoted as C or the pi. So, if AS is greater than 0, so we say 1 and 2 are the completely spreaded by the 3. So, medium 3 will displace the medium 2 and spread the medium 1, it is complete spread. Now, consider the second situation where gamma 1, 2, 3 is the positive. It means there is attraction between 1 and 2 in the medium 3. So, gamma 1 3 plus gamma 2 3 should be greater than gamma 1 2. It means the interfacial energy is not enough to the spread medium 3 and the medium 1. So, in this case the contact angle are spreading between the 0 and 180 degree. So, here we say S is less than 1, you can say the partial spreading or partial wetting. Now, how to calculate the work of adhesion here? So, if you want to calculate the, if you remember the last expression W12 equal to W gamma 1 plus gamma 2 minus gamma 1 2. So, this is the 2 medium 1 and 2, you want to separate it. So, first let us consider it is we are going to have the cohesive. So, WC W11 will be 2 times of the gamma 1, and this work of adhesion is approximately considered as the geometric mean. So, W11 we are considering the geometric mean of the W11 into W22, and W11 we can write this is gamma 1, W22 we can write the gamma 2. Now, if you consider the surface tension of a molecule, it has both the component gamma equal to the gamma p plus gamma d. It has the polar component plus it has the dispersive component. So, if you write gamma like gamma p plus gamma d, so you can write W12 is equal to twice into gamma 1 dispersive, gamma 2 dispersive to the power half plus 2 into gamma 1 polar into gamma 2 polar to the power half. So, I have listed surface tension of the common liquid. So, you also saw in the last slide surface tension of water is 72, but it has both the component polar, it is more polar and less dispersive. If you go for the ethylene glycol, it is having both polar and dispersive component. If you go for formamide, it again has both polar and dispersive component. You go to toluene, it is mostly having the dispersive component, very less polar component, but if you go for other nonpolar solvent like hexane, it only have dispersive component, no polar component. Same for bromonaphthalene and for diiodomethane. Now, we will quickly see, let us say you are having a hexane water system, hexane and water, you want to calculate the gamma 1 2. How will calculate gamma 1 2? Gamma 1 2 will be gamma 1 plus gamma 2 minus W 1 2. And in the last slide we saw how to calculate this W 1 2. W 1 2 will be twice of the interaction of the dispersive to the power half into twice of the interaction of the polar to the power half. Now, interestingly, if you see the hexane here, in the hexane it does not have the polar component. So, the polar terms will be 0. So, we will have only dispersive term gamma 1 plus gamma 2 minus 2 into gamma 1 का dispersive, gamma 2 का dispersive to the power half. So, we quickly calculate here. So, its value is coming out to be 52.2 millinewton per meter. So, in this way you can quickly calculate the value of interfacial tension between solid liquids or between two immiscible liquids. So, here I conclude this lecture. So, here we started with how the work of adhesion is calculated, and then from the work of adhesion we related the work of adhesion with the surface tension and surface energy. Then we saw how the unit change in the area or unit change in the length is related with the surface energy with two examples. One was the soap bubble, otherwise the an unit area A. Then from there we discussed how to calculate enthalpy, entropy, Gibbs free energy from the surface tension data, or you can say from thermodynamically we correlated how the surface tension changes with the temperature, and we observed that if you are increasing the temperature, there is going to be increase in the entropy at the interface region. If it is entropy is increasing means there will be decrease in the surface tension or the surface energy. Then we saw the how to calculate the interfacial energy between two immiscible solid liquid or the solid or the two immiscible liquid liquid or the solid liquid, and we derived that interfacial energy is the sum of the individual surface energy minus the work done at the interface between these two, and then finally we calculated the interfacial energy of one hexane water system. So, thank you.